Ranked 10th, calcite, documented glow across continents. Among all minerals known to exhibit fluorescence, few are as thoroughly studied or as widely distributed as calcite. It has been recorded on every continent, forming in limestone caves, sedimentary basins, hydrothermal veins, and even biological systems such as coral and marine shells. Its chemical formula is familiar to every geologist, yet under ultraviolet light, calcite becomes more than a carbonate structure. It becomes a tool. Calcite fluoresces in a spectrum of colors depending on its trace element inclusions: red when activated by manganese, blue when influenced by lead, and yellow or green in the presence of rare earth elements. These responses vary under long-wave and short-wave UV sources, making calcite one of the most versatile minerals for fluorescence classification. In controlled conditions, some specimens also exhibit weak phosphorescence, a slow fading glow that persists after the UV source is removed. This property has made calcite a staple in both academic research and field identification. The first systematic observations of calcite's fluorescent behavior date back to the early 20th century, particularly from collections in Franklin, New Jersey, and Elmwood, Tennessee. These sites remain reference points in mineralogical literature for shortwave fluorescence in calcite. Today, calcite continues to serve as a calibration mineral in UV testing, helping differentiate similar-looking specimens in both museums and mining environments. While common in composition, not all calcite fluoresces. The effect depends on a precise combination of structural purity, lattice distortion, and chemical substitution. For this reason, glowing calcite specimens are routinely labeled by source locality, such as Terlingua type, Texas, Pew Quarry, Ohio, or Leaping Mine, China, to prevent commercial misrepresentation. In gemology, calcite has limited value as a cut stone due to its softness, Mohs hardness 3, and perfect cleavage. However, as a scientific specimen or educational reference, it remains essential. The mineral's optical properties, such as birefringence and double refraction, further distinguish it within crystallography labs. Among glowing minerals, calcite stands out not for its rarity, but for its reliability. It is used not because it is beautiful, but because it is consistent. Its fluorescence is not anecdotal. It is measurable, reproducible, and cataloged. And in a field where subjective beauty often drives attention, calcite's value lies precisely in its objectivity. Ranked 9th. Opal, localized fluorescence in hydrated silica. In controlled ultraviolet conditions, a select group of opals reveals a weak but measurable glow, distinct from the more familiar play of color phenomena often seen in daylight. This luminescence is not universal across the species, but has been confirmed in specific opal types collected from volcanic and sedimentary deposits. Under long-wave UV light, some white opals emit a pale green or bluish fluorescence, while black or fire opals from the same locality may remain entirely non-responsive. The mechanism responsible lies not in crystallinity, opal is amorphous, but in the chemical environment during its deposition. Trace elements, such as uranium and rare earth metals, as well as organic carbon compounds, have been identified as potential activators of fluorescence in opal matrices. These elements are introduced during low-temperature silica precipitation, often in association with rhyolitic tuff or volcanic ash layers. Unlike fluorescence in calcite or scheelite, which can be strong and consistent, the optical response in opal is generally weak, highly variable, and sometimes imperceptible without filtered equipment. Fluorescent behavior has been most reliably documented in material from Virgin Valley, Nevada, USA, Coober Pedy, South Australia, and certain hydrophane opals from Ethiopia. However, within a single mining site, only a small percentage of extracted specimens will demonstrate the effect. For this reason, fluorescence is not employed as a diagnostic criterion in gemological laboratories when identifying opal, though it may be noted in technical reports for academic or provenance purposes. Synthetic and stabilized opals further complicate this assessment. Due to their porous structure, hydrophane opals are prone to absorbing dyes or polymeric substances during treatment. These additives can produce secondary fluorescence not representative of the original material. As such, any glow observed in commercial opals must be interpreted with caution and verified against untreated reference samples. In scientific contexts, fluorescent opals are studied less for their visual impact and more for their geochemical insights. Their trace element composition can contribute to reconstructing paleo-environmental conditions, hydrothermal evolution, and silica mobility in low-temperature depositional systems. When cataloged alongside host rock data, these stones provide subtle yet valuable insights into groundwater chemistry and the presence of uranium or organic acids during mineralization. The glow in natural opal, when present, is neither bright nor stable. It is conditionally dependent on wavelength, orientation, and internal composition. But when detected under controlled light, it affirms a key principle in luminescent mineralogy, that the absence of crystalline order does not preclude optical response. Within a hydrated amorphous network of silica, specific opals can briefly interact with ultraviolet energy in a quantifiable and repeatable manner under laboratory conditions. This response, though limited in intensity, situates opal within the broader category of glow-capable gemstones, not for what it reveals to the unaided eye, but for what it proves in calibrated observation. Ranked 8th, Autunite, radioluminescence in hydrated phosphate minerals. Autunite is a hydrated calcium uranyl phosphate with a layered crystal structure and a well-documented fluorescent response under ultraviolet radiation. When subjected to UV light, particularly long-wave, Autunite emits a bright green glow, often visible to the unaided eye even in low irradiance environments. This glow originates not from structural defects or trace element substitution, but from the presence of uranium in its oxidized form, UO22+, also known as the uranyl ion. The mineral forms through the weathering and oxidation of primary uranium-bearing minerals, such as uraninite or pitchblende. In the presence of phosphate-rich fluids in favorable pH conditions, Autunite precipitates as tabular or platy crystals, often in radial clusters or crust-like coatings on rock surfaces. Deposits have been recorded across North America, Europe, and parts of Asia, with notable specimens from the Czech Republic, France, its type locality in Autumn, and the western United States. What distinguishes Autunite among luminescent minerals is not the strength of its glow, but the mechanism that produces it. Radioluminescence, the emission of visible light due to radioactive decay, is a defining property of this material. In Autunite, both fluorescence and low-level radioluminescence can co-occur, especially in dark-adapted settings. Under daylight, this behavior is masked by the mineral's natural yellow-green coloration, but under UV sources, its fluorescent emission is immediate and intense. Despite its visual appeal, Autunite is not suitable for ornamental or personal use. The uranium content typically ranges from 45% to 60% by molecular weight, placing it in the category of radioactive minerals that require controlled handling. Regulatory standards in most countries prohibit the commercial sale of high-grade Autunite specimens without radiation assessment. Museums and academic institutions that display Autunite do so under protective casing, and prolonged exposure is avoided during curation or research. In mineralogical studies, Autunite serves as both a fluorescence reference material and an indicator of secondary uranium mobility. Its presence signals oxidative alteration zones and can guide exploration for deeper, primary uranium ores. Geochemically, the formation conditions of Autunite also provide insight into fluid chemistry, redox gradients, and weathering duration in granitic or volcanic environments. The mineral's hydration state is another key variable. Autunite loses water readily when exposed to dry conditions or elevated temperature, converting to meta-autunite, a structurally related but optically less intense phase. This instability limits long-term preservation outside climate-controlled environments and contributes to its classification as a mineral of academic rather than commercial significance. In the context of luminescent gemstones, Autunite holds a distinct position. It is not cut, traded, or worn. Its glow is not ornamental but diagnostic, a byproduct of nuclear chemistry rather than aesthetic design. Still, its visibility under UV, coupled with its role in uranium mineralogy, ensures that Autunite remains a critical reference point in the study of naturally glowing minerals. Ranked 7th, Scapolite, ultraviolet emission in metamorphic silicates. Scapolite represents a solid solution series between mariolite and meionite, both tectosilicates formed under high-temperature metamorphic conditions. Though generally classified by composition and optical properties, certain scapolite specimens exhibit a distinct photoluminescent response when exposed to ultraviolet radiation. The fluorescence, most commonly observed under long-wave UV, appears in hues ranging from violet to orange, with occasional pinkish tones. Documented occurrences of fluorescent scapolite have been reported from regions with complex metamorphic histories, including Myanmar, Afghanistan, Tanzania, and Madagascar. In these settings, scapolite forms as prismatic crystals within gneiss, marble, or calcsilicate rocks, often in association with plagioclase, garnet, or diopside. Luminescence in scapolite is not universal, but localized to specimens containing specific trace element activators, typically manganese or rare earth substitutions within the aluminum silicate framework. Compared to well-known fluorescent minerals like fluorite or scheelite, scapolite's glow is less intense but more color variable. Spectroscopic analysis has shown that the emission bands can shift depending on the relative proportions of the mariolite-meionite series, with high mariolite content often correlating with stronger violet fluorescence. Additionally, some scapolite crystals exhibit persistent luminescence, emitting light briefly after the UV source is removed. This afterglow, though subtle, is measurable under laboratory conditions and adds a secondary dimension to the mineral's optical behavior. In the gem trade, transparent scapolite is occasionally faceted as a collector stone. However, its low hardness, Mohs 5.5 to 6, imperfect cleavage limit its suitability for mainstream jewelry. Fluorescent varieties are rarely seen in commercial circulation, and when present, their glow is typically considered a visual curiosity rather than a defining trait. Nonetheless, these pieces are sought after by mineral collectors and fluorescence specialists due to their relatively low abundance and photonic diversity. Scientific interest in scapolite extends beyond gemology. In petrology, the mineral serves as an indicator of metasomatic processes, particularly those involving the mobility of chlorine, sulfur, and sodium in crustal fluids. Its fluorescence, when present, can serve as a non-destructive tool for tracking compositional zoning or fluid rock interaction histories within metamorphic terrains. The photoluminescence observed in scapolite is neither widespread nor guaranteed to be present. Still, when present, it reinforces the broader conclusion drawn from UV-reactive minerals, that glow is not exclusive to a mineral group or crystal class. Even within a series defined by ionic substitution and thermal recrystallization, specific structural alignments can trigger visible emission when exposed to high-energy light. Scapolite does not dominate fluorescent mineral collections, nor does it appear frequently in gemstone catalogs. Its glow remains niche, restricted to informed observation in particular localities. However, within that narrow scope, it holds value as a visual confirmation of chemical variance and as a subtle example of metamorphic complexity captured in silicate form. Ranked 6th, Fluorite, reference standard for fluorescence in halide minerals. The term fluorescence derives its name directly from this mineral. Fluorite, a calcium fluoride compound, is the reference material against which luminescent response in other minerals is often measured. Its role in scientific mineralogy extends beyond classification. It defines the behavior of minerals. Fluorite forms in a wide range of geological environments, hydrothermal veins, sedimentary deposits, and contact metamorphic zones. It crystallizes in the isometric system and typically occurs as cubic or octahedral crystals. Under ultraviolet light, particularly shortwave UV, fluorite emits visible luminescence in various colors, most commonly blue or violet, but also green, yellow, and red, depending on the presence and concentration of activator elements. The most widely documented activator is europium, though rare earth elements such as yttrium, samarium, and terbium may also contribute. The fluorescent response in fluorite is attributed to electron transitions between energy states induced by UV excitation. The emission wavelength depends on both the elemental activator and the degree of structural distortion in the crystal lattice. Specimens from Illinois, USA, Asturias, Spain, and Shizuoka, Japan, have become benchmarks in luminescent mineral collections due to their intense and stable glow under UV exposure. Not all fluorite fluoresces. Color alone is not a predictor of UV response. For example, specimens with vivid daylight color may appear inert under ultraviolet light, while colorless crystals may emit strong blue fluorescence. The variability stems from subtle differences in trace element content and growth conditions. Even within the same locality, fluorescence can differ dramatically from one crystal pocket to another. In industrial and academic settings, fluorite is used to calibrate UV lamps, study energy transfer mechanisms, and demonstrate electronic transitions in solid-state physics. Its stability under repeated excitation makes it suitable for laboratory demonstrations, museum exhibits, and reference spectroscopy. Some samples also show thermoluminescence or X-ray-induced glow, although these behaviors are less commonly used outside of controlled testing. The mineral has little relevance as a gemstone due to its low hardness, Mohs 4, imperfect cleavage, which makes it prone to damage. However, in the study of naturally glowing materials, fluorite holds foundational status. It remains one of the few minerals whose name and behavior are permanently linked in both scientific terminology and field practice. Fluorite's glow is not symbolic, nor is it rare in the absolute sense. It is functional, an effect defined by measurable physics and reproducible conditions. Among minerals that respond to ultraviolet light, fluorite stands out for its clarity in structure, response, and role. It does not merely glow, it defines what glowing means in mineralogy. Ranked 5th, Scheelite, diagnostic fluorescence in tungstate ore systems. Scheelite, chemically identified as calcium tungstate, occupies a central position in both mineral exploration and fluorescence-based identification. Unlike many glow-capable minerals that emit light incidentally, scheelite's ultraviolet response is used deliberately in the field to locate ore deposits. Under shortwave UV light, the mineral emits a bright blue-white glow, sharp, immediate, and easily distinguishable in contrast to its typically tan or beige appearance under visible light. The luminescence is linked to the presence of the tungstate ion within a tetragonal crystal structure. When exposed to UV radiation, this anionic group undergoes an electronic excitation that results in the emission of visible photons upon relaxation. This photophysical behavior is consistent across many localities, making scheelite a reliable indicator mineral during tungsten exploration, particularly in quartz veins and skarn-hosted deposits. Geological occurrences of scheelite are widespread. It forms in medium to high-temperature hydrothermal systems and contact metamorphic zones, often associated with minerals such as wolframite, cassiterite, molybdenite, and fluorite. Primary sources include China, Austria, Vietnam, Portugal, and the western United States, where scheelite-bearing veins have historically supported both wartime and commercial tungsten production. In mineralogical practice, scheelite's glow under UV is strong enough to be detected in daylight using filtered lamps. This has made it an essential tool in rapid field screening, especially in remote or mountainous terrain where laboratory access is limited. The blue-white fluorescence is so distinct that it can be used to distinguish scheelite from non-glowing minerals of similar appearance, such as feldspar or barite. While the mineral has been faceted into collector gemstones, its practical hardness, Mohs 4.5 to 5, and brittleness limit its suitability for wear. Its primary value lies in its economic and geochemical relevance. In academic settings, scheelite is used to study electron transfer processes in inorganic complexes, and in materials science, synthetic analogs are explored for scintillation applications in radiation detection. The fluorescence in scheelite is not subject to wide variability. Unlike minerals that depend on trace element activation, the glow in scheelite is intrinsic to its crystal structure. This internal consistency allows it to function as both a field indicator and a reference specimen in UV-based mineral studies. Its reliability stands in contrast to less predictable fluorescent behavior seen in silicates or carbonates. Scheelite's luminescence serves no decorative function. It is not marketed for glow. It is employed. In exploration, in education, in ore geology, the mineral's light under UV is a signal, functional, quantifiable, and constant. Ranked 4th, Powellite, rare phase. Luminescence in molybdate systems. Powellite, the calcium molybdate analog to scheelite, exhibits one of the most visually striking luminescent responses in the mineral kingdom. When exposed to shortwave ultraviolet light, it fluoresces with an intense yellow-green emission, often described in technical literature as neon-like. This response is both immediate and high contrast, particularly in samples from basalt-hosted cavities or contact metamorphic zones. The mineral belongs to the molybdate group, crystallizing in the tetragonal system with a chemical formula. Structurally, it is isostructural with scheelite, but the substitution of molybdenum in place of tungsten alters both its physical behavior and its optical characteristics. The glow arises from charge transfer transitions within the anion complex, which under UV excitation releases visible photons in the yellow-green spectrum. This emission band is sharply defined and consistent across well-preserved specimens. Powellite is considered rare. It forms under specific geochemical conditions, typically in oxidized zones of molybdenum-bearing deposits or in association with zeolite-bearing volcanic rocks. Notable localities include Nasik and Pune districts in India, as well as select pegmatitic environments in the western United States. In many cases, Powellite appears as microcrystalline coatings or nodules within vugs, often accompanied by minerals like apophyllite, stilbite, and quartz. Despite its intense glow, Powellite remains absent mainly from commercial gemstone markets. Its softness, Mohs hardness approximately 3.5 to 4, and perfect cleavage render it unsuitable for cutting or wear. Furthermore, its occurrence is often too localized and fine-grained to be extracted on a large scale. Nonetheless, it holds high value within specialized fluorescence collections, particularly due to its reliable and dramatic UV response. In mineralogical contexts, Powellite is sometimes misidentified as scheelite due to their structural similarity. However, under UV light, the difference becomes immediately apparent. While scheelite emits a blue-white fluorescence, Powellite's glow is shifted toward the green-yellow range, a diagnostic feature that allows for field distinction using portable UV lamps. In laboratory settings, it also serves as a reference standard for molybdate luminescence and has been studied for its photoluminescent and scintillating properties in materials science. The fluorescence in Powellite does not rely on impurities. It is intrinsic to the molybdate component itself, requiring no external activators. This makes the mineral a model example of host structure-based luminescence, in contrast to fluorescence arising from rare earth or transition metal substitutions in other minerals. Within the framework of glow-capable minerals, Powellite occupies a niche position. It is not as abundant as calcite, nor as functionally applied as scheelite, but when encountered, its optical behavior is both unambiguous and scientifically significant. Its visibility under UV is not decorative. It is diagnostic, rooted in predictable molybdate chemistry, and expressed through one of the most saturated natural emissions known among mineral species. Ranked third. Willemite, zinc silicate luminescence in oxidized skarns. Willemite, a zinc silicate mineral with a formula, is recognized globally for its exceptionally bright green fluorescence under shortwave ultraviolet light. The response is not only immediate, but often intense enough to be visible in ambient lighting. This has positioned Willemite among the most demonstrable naturally fluorescent minerals known, particularly in educational, curatorial, and field identification contexts. The mineral crystallizes in the trigonal system and typically forms in granular to massive habits within zinc ore bodies. While non-fluorescent Willemite exists, the green glowing variant is most strongly associated with secondary oxidation zones, where sphalerite and franklinite undergo alteration. In such environments, Willemite forms through metamorphic reworking, frequently coexisting with calcite, franklinite, and zincite. The most famous occurrence is Franklin and Sterling Hill, New Jersey, USA, where Willemite specimens exhibit a fluorescence so strong that entire outcrops can appear illuminated under portable UV light. This locality is considered globally significant not only for the strength of the emission, but also for the scientific study of mineral fluorescence. Similar but less intense examples have been documented in Namibia, Belgium, and Mexico. The fluorescent behavior in Willemite results primarily from the presence of divalent manganese ions, substituting for zinc within the silicate lattice. These activator ions absorb ultraviolet photons and re-emit them as visible green light, typically centered around 530 to 550 nanometers. The intensity of this emission is affected by the concentration of activators, lattice symmetry, and the presence of quenching elements like iron. Unlike many luminescent minerals, Willemite does not require rare earth elements to achieve its glow. Beyond mineral collecting, Willemite holds industrial and scientific interest. Synthetic versions have been employed in early cathode ray phosphors and are being investigated for potential applications in optoelectronics and scintillation materials. In mineral exploration, its glow continues to assist in locating oxidized zinc deposits, particularly in regions where field lab equipment is limited. Though faceted specimens exist in private collections, Willemite's moderate hardness, Mohs 5.5, and variable transparency make it an unconventional candidate for jewelry. Its primary value remains scientific and visual, a material that demonstrates how simple silicate frameworks can interact with ultraviolet radiation in complex, quantifiable ways. Willemite's fluorescence is more than a visual effect. It's a stable and repeatable expression of its internal chemistry. Its presence in a mineral suite can inform geochemical history, indicate post-depositional oxidation processes, and distinguish zones of economic zinc concentration. Under ultraviolet light, its glow is not symbolic, it is instructive. And in a field that often depends on subtle optical clues, Willemite provides certainty in green. Ranked second, Sodalite, reversible light responsiveness in tenebrescent feldspathoids. Sodalite, a tectosilicate mineral within the feldspathoid group, occasionally exhibits fluorescence under ultraviolet light. In most geological contexts, its luminescence is limited, faint, and has a purple tint, often inconsistent in intensity. However, in specific natural variants, particularly Hackmanite-bearing Sodalite, the mineral demonstrates two distinct and scientifically verified optical behaviors: UV-induced fluorescence and tenebrescence, or reversible photochromism. Hackmanite refers to sulfur-rich Sodalite with a unique capacity to change color in response to UV exposure. When exposed to shortwave UV light, the mineral transitions from pale gray or pink to a saturated violet or deep rose hue. Upon removal from the UV source, this induced coloration gradually fades in darkness or returns to its baseline under incandescent light. This process is repeatable and non-destructive, governed by the movement of electrons within sulfur-related defect centers in the crystal lattice. The tenebrescence in Hackmanite is not anecdotal. This is well documented through spectroscopic analysis and electron paramagnetic resonance studies. The color change originates from photo-induced electron transitions between valence states of sulfur and subsequent trapping in anion vacancies. These mechanisms are stabilized by the mineral's cubic symmetry and low iron content, which limits luminescence quenching. In addition to photochromism, many Hackmanite specimens also fluoresce under UV, typically emitting violet or orangish-pink light. This fluorescence, while weaker than that observed in Willemite or Scheelite, remains visible to the naked eye under controlled conditions. The combination of fluorescence and tenebrescence in a single specimen makes Hackmanite one of the few minerals with dual optical responsiveness, qualitatively different from static fluorescence. Primary occurrences of naturally tenebrescent Hackmanite include remote deposits in Afghanistan, Myanmar, Greenland, and the Kola Peninsula in Russia. Specimens from these sources are evaluated based on their tenebrescent intensity, UV fluorescence response, and fading half-life under ambient conditions. Synthetic Hackmanite has also been produced for research and decorative purposes, although its color dynamics and durability differ from those of untreated natural samples. The mineral has seen limited use in gemology due to its relatively low hardness, Mohs 5.5 to 6, and cleavage characteristics. However, its capacity for light-induced transformation has made it a focus of research on optical materials, with studies exploring potential applications in UV detection, bright pigments, and reversible display technologies. In academic settings, Hackmanite serves as a model system for understanding charge transfer dynamics in mineral lattices. Unlike fluorescence, which is fixed and instant, Tenebrescence in Sodalite offers time-dependent visual evidence of structural behavior under UV influence. The glow fades, returns, and evolves with exposure, a feature not replicated in most mineral species. In the context of naturally responsive gems, Hackmanite-bearing Sodalite stands out as a dynamic system, observable in both the field and the laboratory, and deeply tied to the fundamental interactions between radiation, matter, and crystal chemistry. First place, Hackmanite, dual-mode luminescence in sulfur-rich sodalite systems. Hackmanite exhibits a convergence of two independently rare optical behaviors, persistent fluorescence and reversible tenebrescence. This mineral, a sulfur-bearing variety of sodalite, possesses a chemical framework that supports both ultraviolet-triggered emission and metastable photo-induced color shifts. Unlike other luminescent materials whose glow is immediate and fixed, Hackmanite responds to light in phases, before, during, and after exposure. Under long-wave UV radiation, Hackmanite emits a visible glow in pink to violet tones, varying by locality and composition. The source of this fluorescence lies in trace manganese activators and sulfur-centered defects within its cubic feld, spathoid lattice. Though moderate in intensity compared to Scheelite or Willemite, the fluorescence in Hackmanite is consistent and detectable in well-preserved samples. Simultaneously, the same exposure initiates a deeper process, tenebrescence. In the presence of shortwave UV or high-energy visible light, the mineral undergoes a color change, shifting from its original state, often grayish or faintly pink, to rich violet or purplish hues. This shift persists even after the radiation source is removed and gradually fades under ambient light, repeating the cycle indefinitely. Among naturally responsive minerals, Hackmanite is one of the few that records its interaction with light over time. The transition is not instantaneous. It develops, stabilizes, and resets, a rare dynamic behavior in solid-state systems. This has placed Hackmanite at the center of studies in radiation dosimetry, optically stimulated luminescence, and photonic memory materials. Documented localities for natural Hackmanite include the Koksha Valley of Afghanistan, the Kola Peninsula of Russia, northern Myanmar, and certain regions of Greenland. Samples from each exhibit variation in tenebrescent depth, fluorescence hue, and color stability, depending on sulfur content, lattice strain, and secondary mineral inclusions. No two sources produce identical optical signatures, making geographic origin a significant factor in scientific classification. The mineral's response to light has attracted attention beyond academia. In controlled environments, Hackmanite has been tested for use in UV detection materials, optically responsive ceramics, and reversible authentication inks. In mineral collections, it is categorized as both a fluorescent and tenebrescent specimen, a dual status rarely assigned in the field of optical mineralogy. In gemological contexts, Hackmanite is occasionally cut and set into display pieces. However, its relatively low hardness, Mohs 5.5 to 6, and perfect cleavage limit its durability. Its commercial presence remains secondary to its scientific uniqueness. Hackmanite does not simply glow. It evolves under light. It holds and releases energy in visible cycles, each tied to the structure of its atomic network. No filter, no coating, no artificial treatment is responsible for what it displays. The glow and the change are both intrinsic, measurable, and reversible, defining characteristics that distinguish it from every other entry on this list. Among minerals that respond to ultraviolet light, Hackmanite is the only one that can be observed in motion, shifting, retaining, and resetting its color in direct response to its exposure history. For this reason, it stands not only as the most complex entry among glow-capable stones, but also as the most instructive.